Okay, so this video is going to talk about the logic of experiments as a research design and why it is such a powerful tool for establishing causation, for helping us become more confident that one thing causes another. We'll see that the way you carry out an experiment makes a big difference, though. So let's start with an example you may have heard before. Data has shown that ice cream sales correlate with crime levels, meaning when ice cream sales are highest, crime is highest, and when ice cream sales go down, crime goes down. They're correlated, which naturally leads us humans to ask, why? Now, one of your friends might propose that eating ice cream causes crime. Like, maybe the sugar rush makes people more impulsive, or maybe long lines at Ben & Jerry's leads to arguments and shoving and fights from people in line for that sweet, sweet chocolate chip cookie dough. And of course, jaywalking is technically a crime, and I bet people cross the street to get into that popular new ice cream shop right before it closes. That would explain the correlation, if ice cream is in fact causing the crime. But one of your other friends might chime in and propose instead that crime causes ice cream sales. After all, when you've just committed some arson, wouldn't you want to celebrate with a delicious treat? And crime includes things like bank robbery. After you pulled off a big bank heist, you've got plenty of money for expensive treats like ice cream that you might otherwise not be able to afford. So crime causes more ice cream to be purchased, says this friend. So we're kind of at an impasse. Which friend is right? Does the first variable cause the second, or does the second variable cause the first? But that's when you chime in with your badass knowledge of psychological science and research methods. What if there's a third variable at play? You heroically exclaim. What if something else is causing both of these variables to correlate without either of them directly affecting the other? So for example, maybe the heat, like the weather or the time of year. Because during winter, it's cold out and fewer people leave their houses, so crime goes down because everyone's staying home. Meanwhile, people are also avoiding ice cream because a cold treat just isn't as good when you're already cold. Meanwhile, though, in summer, everyone's out and active and there's just more opportunity for crime to occur. And of course, on hot days, ice cream is the perfect snack to cool off. So sure enough, the weather or the season, that could explain our consistent correlation between ice cream sales and crime without either of these variables directly affecting the other. We call that a third variable. A third variable might be at play. And not just heat. It could be any variable, including ones we hadn't thought of. Like, even if both friends are wrong and you are also wrong about heat being the cause, there may be some other third variable that explains it. So we call this the third variable problem, and it's forever going to be a problem if all we have is correlational data that's tying two things together. The correlation alone will never tell us why. It'll never let us distinguish between an infinite number of possible causal explanations. So what we need is a different method entirely, something much more powerful than just measuring some variables and finding a correlation. And the best method, of course, the best tool we have, is to do an experiment, to use a true experimental design. In an experiment, we don't just measure or describe something about the world, we actually manipulate things. We control the situation directly as researchers. Now, we'll see in a minute why this is also going to be the most reliable way to address the third variable problem and rule out all the third variables, even the ones we never thought of. But first, just a quick simple example of an experimental research design. Let's say we found a correlation between, say, anger and criminality. Like maybe studies have found that people with a propensity towards anger are incarcerated at higher rates than those who don't anger easily. And maybe some other studies have interviewed people right after they committed crimes and found that it was most common for them to self-report being angry at the time. So there's a correlation out there maybe. Maybe our suspicion is, I think anger is actually a causal factor in the criminality. I think anger causes crime. So we want to test that. We want to test if one of the variables, anger, causes the other variable, crime. To test it in an experiment, then, we as researchers have to manipulate the thing that we think might cause a difference in the other thing. So we have to manipulate anger in this case because we think anger is doing the causing, is doing something to the other variable. So say we take 150 people, we randomize them into two groups. Maybe we make half of those people angry and we make the other half not angry. In that case, we manipulated one variable. Then we measure the other variable, the outcome. In this case, whether the anger group commits more crime in the next week. Maybe that's one way to measure it. Or maybe we measure whether the anger group is more likely to take a $20 bill that we leave sitting out on the experimenter's desk. Right? We have to find some way to operationalize criminality for our study. But that would be an experimental design testing whether anger causes crime. Admittedly, it's a simplistic example, but the key point is we manipulated one variable and then measured the other. And we manipulate the one that we think is doing something to the other. So this is where the terms independent and dependent variable come from. The independent variable is the one the experimenter manipulates. This is the one you think causes differences in the other variable. Whereas the dependent variable is the thing you are measuring, so the outcome. It's what you think is going up or down, happening or not happening because of differences you made in the independent variable. Note how I've highlighted cause here in because, right? So unlike correlational research, experiments are a way to actually test causation to see if one thing causes another. One mnemonic that might help you remember these terms is for the dependent variable, we could say each person's value depends on what the independent variable is set to for them. It depends on what group they were assigned to. Whereas the independent variable, given that the researchers are manipulating it, like you're assigning people into different levels of this variable, you can think of it like the experimenter has some independent control over that variable, some independent control over the independent variable. So let's take another simplistic example. Does beer cause sleepiness? Let's do an experiment. First, we might randomly split, say, 250 college students into two groups. The experimental group, we make them drink 3 beers. The control group, we make them drink 3 waters. Then we measure their sleepiness as an outcome to see if the experimental group gets more sleepy. Now we might ask ourselves, what's the independent variable here and what's the dependent variable? You could pause the video now and identify those. So my hint here is to always look first at what the experimenters manipulated. That's the independent variable. Since they directly chose what people drank, beer or water, that's the independent variable. You could label it beer versus no beer, beer or water, or just what they drank, whatever you want for the name of that variable, but that's the independent variable. The dependent variable then is sleepiness. Like we want to know if sleepiness depends on what they drank, hence the word depend in there, right? Dependent. And of course, to get into the nitty-gritty, we would still have to figure out an operational definition for sleepiness to decide how we'll measure that variable in our particular study. Like maybe they're in a sleep lab during the night of the study, or maybe we just track their sleep with a smartwatch, or maybe we ask them to self-report what time they slipped into bed that night, right? You have to think about how to measure the variables still. Now let's practice another example of an experimental design. For a long time, many people assumed that inner emotions lead to outward expressions of emotion. So if you're in a good mood, that causes you to smile. Mood causes smiling. But some people, like Darwin, proposed other theories of emotion, including something called the facial feedback hypothesis. The idea that if you force yourself to smile, it will put you in a better mood. Or if you frown a lot, it'll keep you in a crappy mood. So rather than a good mood causing smiles, this would be asking, does smiling cause good mood? And how would we test this? Well, we identify which variable we think is causing something, which variable we think is doing something to the other variable, and that's the one we manipulate, the independent variable. So that would be smiling. Well, okay, we'll randomly split, say, 150 people into two groups. An experimental group forced to smile for 5 minutes, maybe by putting a pin in their mouth a certain way that causes smile muscles to activate. And then a control group is forced to not smile for 5 minutes, but maybe they still have to hold a pin in their mouth a different way just to keep that kind of similar. Then we measure both groups, we measure their mood at the end to see if the experimental group, the smiling group, shows a higher mood score. Now, as before, we can ask here, what's the independent variable? Again, you might pause the video and practice that. Well, facial expression is the thing we manipulated as researchers. It's the thing we assigned them to do in a certain way. So that's the independent variable. The values that variable can take were smile or no smile. And then what's the dependent variable? Well, that's the other variable. So the thing we're measuring afterward, their mood. We want to know if mood depends on the smiling. Now, just a quick critical thought, kind of a side note, but a critical thought check here. This was indeed an experimental design, which is our main way of getting at causation questions in science. But it still has to be a good experiment. Like, we found a mood difference here between our groups, but did we really measure whether smiling caused the mood difference that we found between the groups? When you saw the lady in that last picture with a pin sideways in her mouth, did it look like a genuine smile to you? Because it turns out forced smiling, just moving the mouth muscles, might be quite different from like genuine smiling. There are different forms of smiles. In fact, a French neurologist named Duchenne showed that some smiles don't just raise the corners of the mouth, they also involve muscles that raise the cheeks around your eyes. So in our study, we measured the effects not of smiling in general, but of a particular type of forced smile, just that one type of smile. For that matter, though, maybe our instructions for the control group were to tell them not to make any expression while they hold the pen in their mouth, and that instruction made them sad, and that's why their mood scores were lower than the experimental group. So while an experimental research design is our way of testing causation between variables, we still have to think about the specifics of how we carry out our experiment if we want to be confident in those results. By the way, just as a side note, the original 1988 study using the pins in mouths, that technique, didn't actually work out when a bunch of independent labs later in the mid-2010s tried to repeat the procedure and replicate that. So it's actually unclear if that particular methodology is a good test of the facial feedback hypothesis. There are, though, a bunch of other studies on that hypothesis, like people injected with Botox, which somewhat paralyzes your frowning muscles, they become slightly slower to process sad or angry sentences, and the amygdala has less activity when they try to imitate angry expressions, things like that. As with most things, the point is a single study, even an experiment, whether the results are positive or null results, a single study alone doesn't answer these big significant questions about how the world works. We need to kind of build science on itself over time. But for now, let's get back to the logic of experiments. So you may have noticed in my examples, I keep saying randomly split people into groups, or randomly make one group do X and the other group do Y. So why is that? Well, using the randomness turns out to be one of our most powerful weapons in research design. If we want to build evidence for one variable causing another, an experiment is the best way to do that. Specifically, we talk a lot about random assignment. That is the term for using a random procedure to assign participants into the different groups, the different levels of our independent variable. So with a random procedure, it means each person has an equal chance of ending up in any group. You, as researcher, are controlling what level of the independent variable each person gets, but random assignment means you're doing that in an unbiased way. Think of it like this. Every person differs from everyone else in myriad ways. We all vary in terms of age, sex, weight, eye color, height, personality, size and shape of the genitals, you name it. Assuming you use enough participants, though, the benefit of random assignment is that it balances all of those variables out pretty much evenly across the groups. Think back to the third variable problem we had with correlational data. There is any number of possible variables that we never thought of that could always explain why X and Y are correlated. But with random assignment, for every single characteristic you can think of, every single variable, the variation in those things will be spread pretty much equally across the groups. So now, I should admit, we can't guarantee this if we have a tiny sample size. But as long as we have a reasonable sample size, this starts to work very quickly and very well, and the larger your sample size, the better. So to see this idea most clearly, let's imagine just a really huge sample. Let's say you've got 1 million people, and you use random assignment to split them into two groups of 500,000 per group. So this is a very large sample size. In that case, you are very, very, very likely, just by probability theory, we can prove, you are very likely to have about half the women in each group. You're also going to have about half the green-eyed people in each group, half the blue-eyed people in each group, half of the short people in each group. Half of the people who are having a bad day will end up in each of those groups. So it kind of evens everything out. If, half of 1% of participants are narcissists or have MS or some other rare trait, you would still end up with that rare trait being split pretty much equally between the two groups. So with enough participants, randomness literally washes out every variable, even the ones we hadn't thought of. And I do say with enough participants because large samples are important. Large samples have less variability, less streakiness. Kind of like how flipping a fair coin 1,000 times is going to get you pretty close to a 50-50 split most of the time, right? 50% heads, 50% tails. You'll be near there after 1,000 flips most of the time. But if you just flip a fair coin 4 or 5 times, you're not as likely to be right around that 50-50 mark. If you flipped a fair coin 10 million times, then you're going to have very, 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 very close to 50% heads. So the whole idea here is that random assignment means the groups start out the same in every way, on every variable. And this is important for the logic of experiments because we want our manipulation, the independent variable, to be the only difference between groups. That way, if one group scores much higher or much lower on the dependent variable, it must be because of our treatment. We can establish strong evidence of causation. That's the fundamental logic of an experiment that makes it so powerful. We can make sure the groups don't differ on any variable, so there's no third variable that could explain our results later on. If someone says our results might come from some people being caffeine users, we can point out that both groups had basically the same number of caffeine users, so we can rule out that third variable. If someone else wonders if our results are due to gender, we point out that both groups had the same gender proportions. Like, every single variable is very likely to be evened out if we use random assignment on a reasonable number of participants. And just to be clear, random assignment ensures that we minimize differences between our groups at the start of the experiment, the beginning. We begin our experiment with the groups having no differences. Then when we introduce the IV as the only difference, right, that's our manipulation, then we can say that would be the only reason we could have any differences. It's the only explanation for any differences in the DV that we find later. But if we're only starting the groups the same, we still have to avoid something else, some other variable other than the IV, becoming different between the groups during our experiment. In other words, we need to make sure we don't introduce other differences during the experiment itself, since those could then be an explanation for our results at the end, rather than the independent variable. Just for example, if the experimental group is spending more face-to-face time with the cute experimenter in order to get their treatment, it might be that additional time with that hottie is what causes any differences in the DV, rather than the actual treatment itself. So these additional variables that unintentionally ended up as a new difference between our groups, they're called confounding variables. You'll often hear it described as a confound. It's an extra variable, an extraneous variable that affects the results. Specifically, it's something other than the independent variable that introduced an unintended difference between the groups. That means any confounds that we haven't fixed, those become alternative explanations for the results that we need to rule out or avoid if we want to be confident that our independent variable causes the changes in our dependent variable. So for example, let's say we're testing something like acupuncture to see if it works to lower people's pain. Maybe someone else started, with a purely correlational study. So they collected some data and found that patients report decreased pain following acupuncture. You probably know some people who have said they feel better after acupuncture. So in that case, acupuncture is associated with decreased pain. So we might be tempted from this correlation to think acupuncture was causing the improvement. We might be tempted to think acupuncture works, even though the theory it's based on is pretty much nonsense that doesn't fit our modern understanding of anatomy at all. And it's really, really tempting to take this correlational data that people often report feeling better after acupuncture and assume that it means acupuncture works. It is just so damn intuitive, right? Our brains, with all their cognitive biases and shortcuts, we make mistakes like this all the time, unfortunately. But as trained researchers, we know that correlational data alone is not sufficient to show that one thing affects another, that acupuncture affects pain. We need an experiment for that, right? So let's set up an experimental study to collect some more data. Now what we might do is randomly assign a bunch of people with pain, some of them into an acupuncture group, and some into a control group that gets no treatment. Or maybe they even get a pill like Tylenol, right? But what if our data then shows that those in the acupuncture group report more improvement than those assigned to the control group? That's an experiment. Should we conclude from that the acupuncture caused the decreased pain? After all, we did an experiment. Both groups started the same thanks to random assignment. And then we added acupuncture or no acupuncture as the only difference between the groups. So surely that has to be the explanation for the lower pain in our acupuncture group, right? But no, we have unintentionally introduced a problem here, a confound. After all, the way we provide the acupuncture introduced a lot of differences between the two groups, other than just acupuncture itself. For example, maybe just spending relaxing time with someone lowers pain, and that's what caused the results. We could test this by repeating the study, but instead of using a pain pill as our control group, we use massage. Does acupuncture do better than massage? If not, then acupuncture might not be doing anything here. It might just be this other variable. But also, there's the placebo effect to consider. For a symptom like pain, we have a lot of mechanisms by which the brain can attenuate the processing of pain signals. Basically, mental factors can make pain less bad. We know that. The placebo effect is when believing that something will help, expecting it to help, makes you feel somewhat better. So maybe that is why people sometimes report feeling better after acupuncture. Maybe it's not the acupuncture, but a placebo effect. So how the hell do you test for that and find out if acupuncture actually works? Like, in a drug study, a medicine study, we can give participants a real medicine pill and some of them a sugar pill, right? An empty one, a placebo. In that case, both groups are going to have an equal placebo effect. Both of them will have equal expectation, and that's what lets us rule it out and be sure that the medicine itself does something. But that's with like drug trials. What do we do for acupuncture, where it's pretty obvious you're getting poked with needles and stuff, right? So with acupuncture, how do you make the equivalent of a placebo pill that causes participants in both groups to believe in it the same amount, like to have the same amount of expectations for it working, all without one of the groups doing actual acupuncture? And the brilliant solution here, which people have done, is something called sham acupuncture, just meaning fake acupuncture. So researchers use non-penetrating needles that don't actually go into the skin, but you feel a poke, so participants still feel it and think that they're being needled, but there's no needling happening. There's no actual acupuncture. Or alternatively, in some cases, needling happens for real, but not in those magical spots that acupuncture theory makes up, the meridians and stuff like that. Now, the best studies are those comparing real acupuncture to sham acupuncture, where both are performed in the same way by the same trained acupuncturist. And what do we find? Sure enough, when we do these good studies with good methodology, it's all placebo effect. Over and over again, we find sham acupuncture works just as well as real acupuncture. The needle poking thing does nothing. It doesn't work. The whole bullshit magical thinking about meridians and locations of the body does nothing, makes no difference, has no effect. Science has shown this very clearly. Acupuncture isn't real, and scientists are now confident from meta-analyses looking at a bunch of these well-designed studies, acupuncture is just a bunch of pseudoscience. Now notice how important it was, though, to think about confounds. After all, prior to the sham studies, we had that basic logic of an experimental design. Randomly assign into an acupuncture group and a no acupuncture group, ensure the groups start out equal, then see if their pain levels differ at the end. But as we saw, our independent variable of acupuncture wasn't the only difference introduced to our two groups during the experiment. There were lots of confounds in our initial design, like relaxing time spent with a person, but also expectancy effects, placebo effects. When we go back and improve the study to remove those confounds, we find an entirely different result, and now realize acupuncture isn't a real thing. So it's really important to get good at spotting and removing confounds to strengthen our conclusions, to have our experiments work well. So let's do another example, just a simple one for fun. We talked about ice cream being correlated with crime, but we know correlation does not imply causation. So we decided to test whether ice cream causes crime using an experimental design. So we randomly assign a bunch of people into two groups, right? That's our usual thing. The experimental group, maybe they get a bowl of ice cream. Yummy! And the control group gets nothing. Womp womp. Then afterward, we measure the crime rate of each group, maybe over the next day, over the next month, whatever it is, some test of crime in the lab, but we're in some way testing whether crime follows one of these groups more than the other. Now, let's say the results of our experiment are that the experimental group, the ice cream group, does commit more crime than the control group. So we might conclude that ice cream caused crime, right? We did an experiment, which is what we need to get evidence of causation. Both groups started the same. But maybe we introduced some other differences during our experiment. Like when our study started, some people were full and some people were hungry, but random assignment should fix that, right? It should ensure half of the hungry people start in each group, half of the full people start in each group, but that's only at the start of the experiment. During the experiment, we filled up our ice cream group. We made them full, but our control group all went quite a while without any food. So we introduced a confound that made an unintentional difference between our groups during the experiment itself. Maybe the control group was just too hungry to go out and commit crime at the end. That would explain why our ice cream group committed more crime, but it's an alternative explanation instead of ice cream itself causing the crime. So we need to address that confound of what I call hunger. A better experimental design might be to feed our control group the same number of calories. Ideally, maybe even the same number of calories in some other, junk food or something like that. That way, if we still find higher crime in the ice cream group, we know the difference is specific to ice cream, not to some confound like how many calories you've had or not had. Except wait, there's still a confound. What if the ice cream group committed more crime than the equal calorie group, not because of ice cream, but because it was a sugary treat? So we might rerun the experiment with 3 groups. Now we have an ice cream group, a group that gets a chocolate bar of the same calories, and maybe a third group that gets the same number of calories from some non-sweet source. Now, if the ice cream group is still higher than crime in the other groups, we might become more confident it's actually ice cream that's causing crime. But what if the first 2 groups both commit the same amount of crime? Then it might be more about sugar in general, or junk food. So you can see here how for some research questions, it may be hard to rule out all the confounds in a single experiment. Fixing one confound may introduce another. So in practice, it generally is going to take a series of many studies, all varying things in slightly different ways, before we start to be confident that, yes, indeed, the independent variable is causing the dependent variable. We may have to keep going back and testing alternative explanations that are introduced as confounds in one way we carried out our manipulation, and then see if we can rule those out and keep trying all the possibilities, rule out all the alternative explanations. So real science, like solid science, it takes a lot of time and repetition and varying things a bunch of different ways until we start to become more and more and more confident that an effect is real. And yes, one variable is causing another to change. An independent variable is causing changes in a dependent variable.